Welcome to class of physics. In previous video we saw about the functional block diagram of IC555 timer and its working. Now we are going to study about the application of Astable multivibrator, that is generating rectangular waveforms and square waveforms. Now take this screenshot as your reference notes. Okay, so here rectangular wave generations. Here is the circuit diagram for rectangular wave generation using 355 timers. So this is the 355 timers. This is the only 355 timer, and the remaining elements we are connecting externally. So as you know, a stable multivibrator is also called as free running multivibrator. It has no stable states and continuously switches between two states without application of any external trigger. The IC355 can be made to work as an astable multivibrator with the addition of three external components, two resistors RA and RB and a capacitor. The schematic diagram is already shown here. Here IC355 can be made as a stable multivibrator by connecting three additional components externally, so that is two resistors RA and RB and a capacitors. Then we can convert, or we can make IC355 as a astable multivibrator, and this astable multivibrator we call it as free running multivibrator because there is no requirement of any triggering pulses to change the states. Itself it is changing the states continuously. So this is brief introduction about 355 timers. Now let's see how the 355 timer is work as astable multivibrators. Okay, I am not going to read these steps. I will explain by using the circuit diagrams. Okay. Yes. Here is the circuit diagram. This part is the timer, that is here. This whole circuit is represented in this box. It's the representation of 355 timers. Now what are the connections? We are going to connect three external components. One is RA, RB and capacitor C to make it as an astable multivibrators. Now how it works? Yes. So I will explain the functional block diagram. It is easy to understand as astable multivibrators. Now there are two comparators. These two are the comparators. These two comparators are connected to a voltage divider. So lower comparator of non-inverting terminal is connected to voltage divider where the supply voltage is 1/3, and the inverting terminal of upper comparator is connected to the voltage divider at this point. So the voltage available here, it is 2/3 voltage. The inverting terminal of lower comparator is connected to trigger, and the non-inverting terminal of the upper comparator is connected to threshold. Okay. So here, now these two are short circuited here. Okay, the terminal 2 and terminal 6 here, 2 and 6, these two are to connected each other because of there is no requirement of any triggers and thresholds. These two are the connected. Then how it is works? Now there is a capacitor. When we switch on the power supply, then this capacitor starts charging, okay, from 0. Now when the capacitor voltage is less than 1/3 voltage, because the non-inverting terminal of the lower comparator is 1/3. According to the comparator working, if the non-inverting terminal or positive voltage is greater than negative terminal voltage, then the output is 1. If the positive terminal voltage is less than negative terminal voltage, then output is 0. So here the positive terminal voltage is 1/3. Until the negative terminal voltage reaches 1/3, the output will be 1 only. Okay. Now up to 1/3 voltage, the output is 1 here. And according to same rule, the upper comparator terminal, this is also at the voltage of 1 by 3 now, less than 1 by 3. So here the output is 0 because the negative terminal voltage is greater than positive terminal voltage. And then these two are supplied to the flip-flops S and R, so set and reset. Now S is 1, R is 0, so that the output will be 1. When output is 1, the Q bar, its invert, it is 0. When it is 0, the output will be 1. Again output will be inverting. On output 1 means it is high. I will draw the diagram here. The output will be high. Now when the voltage at this capacitor is reaches 1 by 3, okay, now here it is 1 by 3 or greater than 1 by 3. That means the negative terminal voltage now becomes equal or greater than the positive terminal voltage. In these conditions, the output of the comparator becomes 0, and here the state is remains same. Okay, for this the output stage is also remains same. There is no change in the voltage until the reset input is changes. So again Q bar is 0, the output is 0, then output is high only. Now it gets charging, and once it will reach 2/3 voltage of this power supplies. That means now here it becomes 2/3 and here also becomes 2/3. In this condition what happens? Now the positive terminal voltage becomes equal or greater than negative terminal voltage. In this condition the output of the upper comparator will becomes 1, but the lower comparator output is 0 only because the negative terminal is connected to trigger. At the trigger the output is 2/3, so that it is 0. Now the state changes. So when R is 1, S is 0, here it becomes 0. When Q becomes 0, Q bar becomes 1. When Q bar becomes 1, now this discharging transistor get activated because this is connected to the base of the transistor, and the base of the transistor gets sufficient voltage, then it can starts conducting. When it starts conducting, now this capacitor starts discharging through this transistor. When it starts discharging, the output now becomes it is 0. 0 means it is lower state. That means now capacitor starts discharging from 2/3 value, 2 by 3 values. When it starts discharging from 2 by 3 values, now again what happens? It becomes less than 2 by 3 at the positive terminal, and the positive terminal is less than negative terminal voltage, then the output will becomes 0. But here also it is remains again 0 only. When the state changes, now the output is remains same until the set is changed. So output is 1, again output is Q bar is 1. When Q bar is 1, the transistor gets discharging and output is 0. This is again 0 only. Now it gets discharged up to the value of 1 by 3. When it reaches the 1 by 3 value, which one? The capacitor reaches 1 by 3 of the voltage, supplied voltage, then what happens? Now this negative terminal value is equal to or less than 1 by 3. It becomes 1 by 3. So what happens now? The output of this comparator becomes 1, but the output of the upper comparator is 0 only. Now when it is set, that indicates it is set. Now the output of the flip-flop is 1. When Q is 1, Q bar becomes 0. When Q bar becomes 0, this will not conduct now. That means the circuit is breaks here. This is not sufficient voltage. For that the output will get now 1. So that means it will change this to the state 1. Okay. So like that the cycle will be continued by changing higher to lower to higher value. So like that we are going to get the rectangular waveforms. Okay. Simple. The thing is here, the capacitor charges between 1 by 3 to 2 by 3 voltage. Only in this range the capacitor charges and discharges. So depending on charges and discharging conditions, we are getting the output as high and low. Now let's see the time constant of these waveforms. Okay, whatever I explained now, so that is the steps here listed. Can take the screenshot. This time period and duty cycles. The capacitor is periodically discharged between 2/3 volt to VCC to 1/3 VCC. The time during which the capacitor charges from 1/3 VCC to 2/3 VCC, that is equal to the time the output is high. Okay. So when the capacitor charges from 1/3 VCC to 2/3 VCC, here waveform is there, 1/3 to 2/3 VCC, the output here, it is the output. This is output waveform. So this graph indicates charging and discharging. Okay. Now it is charging from 1/3 VCC to 2/3 VCC, then the output is high or 1, and then that is given by the time constant TC. TC indicates time constant for charging. It is 0.69 into RA plus RB, because the capacitor charges through these two resistors RA and RB. Next, the time during which the capacitor discharges from 2/3 VCC to 1/3 VCC is equal to the time output is low and is given by TD. TD indicates time constant during discharge. Time during discharge 0.69 to RB into C. So now it get discharging from 2/3 VCC to 1/3 VCC. Okay, from here to here. So in this condition the output will be low. This is the output, low output, and again it starts charging from 1/3 to 2/3. So here it is a charging and discharging. So like that, when it is charging and when it is discharging. Okay. So this is the output waveform. Then what about the total time period? The total time period is sum of time of charging and time of discharging. So it is 0.69 RA plus 2 RB into C. Now we have to add these two equations, then we get the total time period. And the frequency of the oscillations, the frequency of this oscillation is given by reciprocal of time period. So reciprocal of time period means this one, 1 divided by 0.69 into RA plus 2 RB into C. Here 1 by 0.69 is 1.45. For that the frequency expression is 1.45 divided by RA plus 2 RB into C. This is the frequency. In this equations there is no term of power supply VCC. Okay. There is no VCC term. So that indicates this frequency, the frequency if not is independent of voltage VCC. Whatever the input voltage you are providing to work the IC, then independent of that the frequency is generating. Next, duty cycle. Duty cycle is the ratio of time during which the output is high to the total time T. It is generally expressed as percentage. Duty cycle means time during which the output is high. So output is high when it is charging. When the capacitor gets charging, then the output is high, so that the time for charging divided by the total time. Time for charging is this one, 0.69 into RA plus RB divided by total time is this one, TC plus TD. For that, after simplification we get RA plus RB divided by RA plus 2 RB into 100. This expression will give the duty cycle of the rectangular wave. Yes. So this is about rectangular wave generations. So next, the same circuit is used for generation of square wave, but we have to modify this circuit a little bit by connecting one more additional external components. So that is here. Yes. Astable multivibrator using 555 timer IC. So here we are going to generate square waves. Here the circuit is modified by connecting this diode, forward diode. Yes. The remaining circuit is same, but here the RA resistor is there. with that we are going to connect one more resistor, so that we call it as pot, the variable resistors. Using this pot we can vary the resistor, so that is connected to the array. Now the whole resistance we call it as resistance RA, and here die. Okay, now we can modify that circuit to produce exact square waves. Okay, what should be the condition here? Here the condition is this RB is equal to summation of RA and the forward resistance of the diode. RB is equal to RA plus forward bias resistance. Forward, I will write here forward resistance, because this diode is in forward bias, so that diode. Now we can generate an exact square wave by varying the pot resistance. Now these two together is a resistance that is equal to RA, and sum of RA and the forward resistance of this diode together is equal to RB. So here this capacitor charges through RA and the forward wire, charges to this resistance and the diode. Now it is charging and discharging like from RB to 7. Oh god, this will discharge through this and charges through this. Now by modifying this circuit we can obtain exact square wave. Okay. So this is about integrated circuits. Now for this it will complete. In next video we are going to study about amplifiers, operational amplifiers. Okay. Now take the assignment questions. Explain the working of IC 555 timer, and also explain how to generate rectangular wave using IC 555 timer. Thank you.